This electricity magnetism unit assignment now starts with question number 1. 3 fields: electric, gravitational, and magnetic fields. We know what causes each of these, right? What causes an electric field? Simple. What causes electric fields? Charge. Do we have electric charge here when we have an electron moving through space? Yes, we do. So we definitely have an electric field. And in fact, we have an electric field whether this charge is moving or not. If we have charge, we have an electric field. What causes gravitational field? This is the easiest one. We talked about this in Physics 20, right? Mass. Does an electron have mass? Yes. Whether it's moving or not, electrons have mass. So there is, whether it's moving or not, there is a gravitational field. Now, there's an what causes a magnetic field? Magnets, but that's not the relevant one here. Charges can cause magnetic fields if they are, charges cause magnetic fields if they're moving. So an electron at rest would not cause a magnetic field, but an electron that's moving at a constant speed would cause a magnetic field. So all 3 of these work for me. If we change this question to say an electron is at rest, then the answer would be A. An electric field and a gravitational field would still be produced, but a magnetic field would not be produced at that point. Number 1. A proton with an energy of 894 electron volts. Remember dealing with that the other day? The electron volt thing last week? Perpendicular to a magnetic field, circular path. As soon as I see perpendicular to a magnetic field with a circular path, the first thing that jumps out to me, at least, is FC equals FM. That's what I always think here. FC is equal to FM. That doesn't mean I'm necessarily going to do that, but when I see a charged particle moving in a circle and I'm given the radius or looking for the radius, one of the two, then this is usually where I start. So let's do that here. Let's say mv squared over r equals qvb. B's cancel. I'm going to say B is equal to mv over qr. Perfect. Sub in numbers. We have the mass of a proton, 1.67 times 10 to the minus 27 kilograms. I don't know the speed of the proton. I do know the charge, by the way, 1.60 times 10 to the minus 19 times R is 3.6 times 10 to the minus 4. Okay, we got to find V. We got to find V. How do we find V? What other information do we have that might allow me to find the speed of a charged particle? Well, there's got to be something else here. Look for something else. Have you done a question like this before? You actually have. But if you haven't done a question like this before, then look for something that you don't normally have, right? If you need to do something that you don't normally do, then look for some information that you don't normally have. What do we not usually have in this? The energy. What kind of energy does this proton have as it's moving? What does anything have? What kind of energy does anything have as it moves? Kinetic. Yeah, it's got kinetic. So let's solve for the speed using kinetic energy. Let's solve for speed. 2 goes up by multiplying 2ek over the mass, and I'm going to square root that. But my problem here now is that I don't know what kinetic energy is in joules. So this is where I do that 1 eV over 1.6 times 10 to the minus 19 joules equals 894 EVs over X joules. You do that conversion that I taught you the other day, right? I can't remember if you have to do that tomorrow or not. I mean, the test isn't even finalized yet, but I think I've got, I don't know if I told you this, I think I've got to cut down to about 29. It's about 29-ish questions right now, and I want to take it down to about 25 questions. I don't remember if there's anything like this even in my list of 29 questions right now. But be ready for it. See, it's fair game now. Cross multiply. let's get an answer for the energy in joules, and then let's take that number for joules and sub it in here to get an answer for speed. And now that I have speed, let's sub it in there to get an answer for magnetic field. (1.20 times 10 to the 1 Tesla. So we're going to express that as 1201. Quite a bit to that, right? But listen, guys, there is no excuse for not starting this question, for not having a legit place to start this question. We know a charged particle is moving in a magnetic field. Whether you can finish it off, maybe you set this up and you're like, I don't know how to get speed. Okay, fair enough. But there's no excuse for not setting this up, right? If we study and we know it, there's no excuse for that. We know what to do when a charged particle goes in a circle in a magnetic field. Okay, we're missing something. All right, so find it. Find another way to find it. If you've done it before, great. Go back to what you've done before. If you haven't done it before, then look for something that you don't normally have, like kinetic energy. And just remember that we have to convert that kinetic energy to joules. All right, next question. Anybody ever seen the movie Hunt for Red October? Awesome movie. It's old. It's like 80s, but Alec Baldwin, Sean Connery. Sean Connery, the Scottish guy, plays a Russian submarine captain who defects with his submarine to the United States. And anyways, awesome movie. Anyways, in that movie, they talk about submarine having a magneto-hydrodynamic propulsion system. It's just a way of making the submarine go quiet. Right? It propels it very, very quietly, which is good because that's how you detect submarines, right? Is by noise. Listen, guys, all kinds of information here about this MHD system. We're not going to read through this in detail. Are you kidding me? Our strategy is skim it. So let's skim it. Pretend we skimmed it at least. Get down here. Look, I don't know what I'm going to use this for down here, but I feel like I'm probably going to use that information somewhere. But whatever. Let's read the question and see. The direction of the electric field between the two charged plates. This is a category 1. We've got to get this question. Which way is the electric field? It points. The electric field always points away from the positive toward the negative. Magnetic field, harder because it's a hand roll thing, right? But the electric field is away from the positive toward the negative. So it's toward the right side of the ship. Another one. What's the electric field strength? So the field direction is this way. The field strength should be pretty straightforward as well. We're just going to say E is equal to delta V over delta D. 170, I should say, over delta D is 0.140. And that gives me tell you in a second here, 1.21 times 10 to the 3 volts per meter or newtons per coulomb. So we're going to express that as 1213. Good. Listen, I don't know. I think I make that a category 1 too. Like, you got to do a calculation, but it's about as straightforward as a calculation as we can do. I think the only reason why you probably wouldn't get that question is that you don't find your information, right? We want to find the electric field between two plates. We know what to do. Okay, so go find the information, and the information is pretty clearly here, right above the question. More, holy cow, it just keeps going with this thing. This one's interesting here. The direction of the electric force on a positive particle. The electric force on a positive particle. Look, we've already established that the electric field points this way. If we have a positive particle, which way would the force be? This is not a magnetic field. This is not a hand rule question. This is the electric field. It is either with the field or against the field. Is a positive particle experience a force with the field or against the field? Carmela, positive particle, force with the field or against it? Are you sure? Positive, the force is with the field. So the electric force on the positive is to the right. And let's do a negative while we're at it here. A negative would experience a force opposite to the field, right? To the left. So the answer has to be either C or D, right? Forces to the right, forces to the left, positive, negative. Now, what about the magnetic force? This is the harder one. This is what makes this question a more challenging question here. What about the magnetic force? For magnetic force, this is a hand rule question now, right? We stick our, if we're doing the positive particle, it's our right hand, thumb, particle, fingers, field. Which way is the particle moving? This is what, when I saw this question the first time, I struggled with this for a second here. Which way is the particle moving? I looked through all the information. It didn't tell me which way the particle is moving. How am I supposed to know which way the particle moves? This is the whole point of the electric field. The positive particle will move to the right because of the electric field. It moves to the right. And then it experiences a magnetic force. Thumb to the right, fingers out of the page, palm points down or toward the rear of the ship. A negative particle, we would say thumb to the left, left hand, thumb to the left, fingers out of the page, palm points down toward the rear of the ship. So both of them would experience forces towards the rear of the ship. It didn't occur to me until after I did this question. Of course, the water with these ions is going to go out the rear of the ship. If you want to propel the ship forward, you got to send the water out the back of the ship. Of course, it has to be. Did that occur to anyone before you did the question? It didn't me, but I did spot that afterwards. But when I saw that, I'm like, oh yeah, okay, like I'm really confident about my answer here now, right? Because it made sense, right? That the water's going to propel out the rear of the ship. Thought it was over. Thought it was done with this one. What are we looking for here now? Oh, we're looking for the force on the sodium ion now. Force on sodium is just QVB. Don't make this one harder than it has to be. Sodium is +1. So that's 1 elementary charge. And the speed, I don't know what the speed is. Go find it. Go find the speed. It tells me here, or did I already calculate that? What's the speed that I use there? Oh, 3 meters per second. Good. I'm looking in this big page of information, and they give it to me in the question itself, right? 3 meters per second. And then we times that by the magnetic field, which is up there, 4 Tesla. Don't overlook the obvious, right? We do have to sometimes go back and find that, but don't overlook the obvious if we're given that. All right, 1.6 times 3 times 4 is, numeric response number 3 is 1.91, no, 1.9. times 10 to the negative 18 newtons. Hey, why do I feel so good about that value? 1918. If you would have asked me when I start this question, before I read this question, hey, what do you think the force is going to be on a sodium ion in an electric field? I'd be like, I got no idea. I got no idea what value it should be. So why, when I have no idea what the value should be, why do I feel pretty good about what I just got? What tells me that I'm probably in the right ballpark here? Not the number per se, because I don't really know. Maybe it makes sense, but look at the answer. Look at whatever you want me to express the answer, 10 to the negative CD, right? So we see 10 to the negative 18. We have a two-digit exponent, right? We know it should be a two-digit exponent there. So I feel pretty good about that. All right, multiple choice number 4. I like this one. This is a tricky one, though. I like this one. Point P has a magnetic field that points to the left. Makes sense, right? Because the magnetic field goes away from the north and toward the south. The value of the magnetic field there, I don't know what its number is, but I know the magnetic field at that point is represented by this little arrow. So get a kind of an idea, a relative idea of the magnitude here. Now down here, we still have the magnetic field, the blue magnetic field that was caused by the north and south pole, but we now have a current carrying wire as well, carrying the electron current. So we want to find the magnetic field caused by that. That's going to be a wired grasp rule, right? The magnetic field caused by a moving charge, caused by a current. We're going to say thumb in the direction of the particle into the page, fingers, the wired grasp rule, going to go this way. Above the wire, my fingers point to the left. So the magnetic field caused by these magnets is to the left, and the magnetic field caused by this wire is to the left. So that means the net magnetic field is going to be to the left. Is it C or D? Both of those show a magnetic field to the left. Is it C or D? What's our answer here? D. How come? How do you know? Yeah. If we said the answer was C, then we'd say, look, the magnetic field caused by the wire is nothing. Like, this is the magnetic field that's just a result of the original magnetic field. But we have the original magnetic field and the magnetic field that's caused by the current carrying wire combining to give me that net magnetic field D. Multiple choice number 5. This is a relationship question. You want to find how the radius is affected by other variables. This is a relationship question. And as all of you know, all of you, some of you who are in relationships, as all of you know, especially if you're in a relationship, then the best way to analyze a relationship is with an equation. So we're going to pick an equation here. Right? Listen, when we see a relationship problem on a test, and there's a good chance you will see that tomorrow, you need to write down an equation. It's as simple as that. If it's a question about a relationship between variables, write down a relevant equation. We want to find a relationship between radius and all these other variables. Charged particle going in a magnetic field goes in a circle. So let's find that relationship with this equation. B's cancel. R is equal to QB goes down and R goes up. MB over QB. All right. If I want to make R smaller, what are the 4 ways that I can try to make R smaller? If I make M bigger, does that make R smaller? No, it's just the opposite, right? Well, Keem, if I make M smaller, then R is going to go smaller, right? What do I got to do to V if I want to make R smaller? If I make R bigger, does R go down? Nope. I got to make V smaller, right? What about Q? If I make Q bigger, does R go down? Yeah, it's a denominator, right? And if I make B bigger, R goes down. So anything on the top, it's a direct relationship with R. Anything on the bottom is an inverse relationship with R. Okay, what's my answer here? I got to use, it's A, isn't it? Increase the strength of the magnetic field, make B bigger. And R is going to be smaller. So A is our answer there. Alpha particle. This feels like a magnetic field problem, so right hand, perpendicular, we're good there. We want to find the radius of the circular path. We just arrived an equation for radius. It's mv over qb. But make sure you use the mass and the charge of the alpha particle. It's 6.65 times 10 to the minus 27 times the speed. I don't know what that is. I got to find it. Okay, go back in my information and find it then. We're not looking for that when we read the question. We're looking, sorry, when we read the information, we're looking for that when we read the question. So 2 times 10 to the 5 over, this is an alpha particle, so 3.2 times 10 to the minus 19 times B. What's the magnetic field? I got to find that too. 0.1 Tesla. Guys, you see what I'm trying to do with these questions with information? Like I read the question. Like it's not quite the first thing I read. I'm skimming the information, right? But the first thing I really read is the question. I'm not stressed about a page of information. I read the question. And typically when I read the question, I'm like, hey, I've done something like this before. What do I need to find? To find the information. Oh, I need the speed. I need the magnetic field. So go find the speed and the magnetic field. When we do this, by the way, numeric response number 4, do this, works out to be 4.16 times 10 to the negative 2. We're going to express that as 4162. Somebody said 4172. Feel like that was just a rounding issue. If you said 4172, you knew exactly what you were doing, but rounded wrong. It's okay to make a mistake, but let's not waste a mistake on a rounding issue, okay? Let's not 4% of the test tomorrow because you round wrong. Let's not waste our mistakes on that. Still that same information. We want to find the direction of the magnetic force. This is an alpha particle going down this way, fingers into the page, so thumb, fingers, palm points this way. The magnetic force would be this way. And the location of the center of the circle would be, well, it's the centripetal force. The magnetic force is the centripetal force, so the center of the circle would be same direction as the magnetic force. So the answer would be B for that one. See how you did on that one. Oh, interesting. Struggled with that one a little bit. Oh, look at this. 26% of you, holy cow, 26% of you said the answer was C. What did you do if you said C? I know exactly what you did. What did you tell me what you did if you did C? Got it wrong. Truer words have never been spoken. You got it wrong. But why did you get it wrong? What did you do to get it wrong? Left-hand rule, right? Left-hand rule. So we got to pay attention, right? I can virtually guarantee if you use your left hand for this, I can almost guarantee you did not explicitly write down RH or LH. It's possible to still make that mistake, but unlikely. Whenever we have a hand rule, we want to write down LH or RH as a refresher, as a reminder as to which hand to use. We're probably not going to make that mistake if we do that. Okay, multiple choice number 7. An alpha particle again passes without deflection. Key word is without deflection. We're going to say Fe equals Fm. QE equals QVB. Q's cancel this time, and we're solving for V. It's E over V. And we've got the electric field and the magnetic field. We do the math on that one, and I would guess either C or D. kind of 50-50. A and B could be right, but less likely to be right. C and D are the more likely ones, and sure enough, the answer is D. 3.41 times 10 to the 5. You did pretty well on that one. Almost there. Two more questions. Number 8. Which of the following diagrams best illustrates the magnetic field around a solenoid? I don't really like the way this is set up because I feel like we've got to go through all of them to see which one works, right? So let's start with A. Sometimes, to be honest, I start with B and work backwards because it feels like when I've got to go through all of them, it feels like the answer is usually C or D. Like they're trying to make me go through, do more work. But I'm going to start with A here. If we're going to do electron current, which I recommend you do electron current, electron current's going up in the back, down in the front, like this, and it's going to go around like this. We're going to say fingers on the word front point down, thumb points to the left. So the magnetic field would be left, and this would be wrong, because the magnetic field above it would be to the right, not to the left. Let's do B. Here we've got electrons going up in the front and down in the back, up in the front, thumb points to the right, magnetic field points to the right inside, and then it goes around like this. Yeah, I think that one looks good, doesn't it? B's our answer there. Good. And lastly, multiple choice number 9. I think that's our last question. Did this quickly at the end of class on Friday. Some people stuck around. Clearly not everybody stuck around when I look at the statistics. Clearly not everybody stuck around. There's at least 40% of you that didn't stick around for this. This is Lenz's law, right? We have a magnetic field, number 1. It's a magnet. We drop the magnet. It's moving downwards, right? When it moves downwards through a conductor, this is not a coil, but it's like one ring of a coil, right? Doesn't matter, it's a conductor. When we move a magnet through a conductor, we generate a magnetic field. A current, I should say. That's Ørsted. That's Faraday that we learned about last week. Magnetic field produces an electric current. But that electric current will produce a magnetic field. We learned that on day 2 of this unit. That was Ørsted. But now we got 2 magnetic fields, magnetic field number 1 and magnetic field number 2. And they have to always act together to, what's the word here? They have to act together to oppose the motion. They oppose the motion, right? So to oppose the motion, if I have a little pretend magnet here, what's the polarity got to be to oppose the motion? This is moving downward. To oppose the motion, I got to push upward on this magnet. What will push upward on this magnet? A north pole right here or a south pole right there? Option 1 or 2? What is it? Somebody said it over here. Is it you, Brady? No? Somebody said it over here. South pole, yeah. Look, if I have a north pole there, that doesn't oppose the motion. That helps the motion. It's going to accelerate at like 15. It violates the law of conservation of energy. It can't do that. It's got to be a south pole to push up. It's moving downwards. The magnetic force has to be upwards, and we have to have a south pole to do that. In order to oppose something moving down, we have to repel it up. If it was opposing something moving up, we would have to attract it coming down. We have to oppose the motion. Downward motion, push up. Upward motion, pull down. All right. Oops. Can't have south and south. South and north. Magnetic field goes from south to north. Now we're going to do the coil a little backwards. Instead of fingers, thumb, we're going to say thumb points downward, fingers on the word front point to the right. The current is going to go to the right in the front and to the left in the back. So the electrons are going to flow from Y to X. C or D is our answer there. If the electrons are leaving Y and collecting at X, if the electrons are leaving Y and collecting at X, the electrons are leaving Y, negatives are leaving Y, then Y becomes, if negatives leave Y, Y becomes, if the electrons come back to X, collect at X, X becomes negative, yeah. So Y becomes positive and X becomes negative. So my answer for that one is D.